All right, so we're in for our last chunk of talks for the afternoon before we have some announcements and things go from there. So, Artur, thank you very much for joining us, and you're going to tell us about web scalability techniques, and yeah, quite excited. Thank you. Woo!
Hi everybody, my name is Artur Ejsmont. I am Head of Platforms Engineering at Yahoo 7 here in Sydney. And I will be talking about scalability today. So I'm very passionate about technology, and if you get to know me better, you will right away know how really passionate I am. I love distributed processing, I love architecture, design, all this kind of stuff. But I think scalability always had like a really special place in my heart. I'm so crazy about this stuff that I actually published a book on scalability. So here it is, Web Scalability for Startup Engineers. It was released last year. It's still very fresh. I would like to think of it as a no-nonsense guide from engineer to engineers about all the basic stuff, all the concepts that you need to know to get started with scalability. So if you're working for a small company, or if you never worked on a distributed system, I think this is really a good place to start to get your head around it. I will be actually giving away a few copies of my book. So I have like a little raffle going on as well. So if you want to participate, just come talk to me later today, or send me an email or whatever, and I will add you to the list, and I will let you know what are the rules, how does it work, and I'll be announcing some winners probably next week. We go for a coffee or whatever. I give you the book. We have a chat. So that's enough about me. Let's see what are we going to talk about today. So first of all, I will start off by talking about state. How do you manage state? Because I think it's a really critical part, and it's kind of like a prerequisite. If you understand how important that is and how to do that, it should be much easier for you to scale. Then I will move over to 3 key scalability techniques. So these are like underlying techniques that you will see in different systems applied in different ways. I will show some simple examples, I will go through challenges, and we'll also go over a scenario. So I have like a hypothetical situation, hypothetical app that we try to build, and we will see how you can apply all these techniques in different places and how you can scale. All right, so let's go. So I figured that I have to start with the main points of the day before you all fall asleep, so I'm trying to capture your attention. I'm happy that it's after the break, so hopefully you got energy going on. So wakey, and let's do it. So I think the most important, did I lose my mic? The most important thing to know is really that managing state is the key challenge of scalability. And if there was one thing that you remember from my presentation today, should be that you should keep your server stateless, and that managing state is really the main challenge. So let's talk about it for a little while. Let's see what is state and how can we avoid it. So first of all, state is all sorts of information, all sorts of data that your servers may need to serve requests. So it will be like the data in the database, user accounts, all this kind of stuff. But there's also other types of states that you need to be aware of and you need to manage to be able to scale. So the most common type of state is HTTP sessions. So users log in, you keep their checkouts, or you keep session state or whatever. And if you want to scale your application code, your web servers, you need to manage this wisely. So my recommendation would be to push it to a distributed data store like DynamoDB or whatever, some key value store or cache like Memcache, Redis, whatever you're already using, whatever you're familiar with, pretty much any data store will work. If you have support for expiration, like time to leave kind of functionality, that's a bonus because you don't have to clean up the data. Alternative approach is to get rid of session altogether, just use cookies, and this is actually what Yahoo does. So most of the properties, they don't have any session. We don't store stuff on servers or in the databases. We just use a bunch of cookies, like maybe 10, 20 different things, use different cookies, just store tiny bits of information, and that's all you really need. So the second type of state that you may face is files. So it will be files that people upload to your servers, and it will be files that you're generating, like reports or whatever. All of this stuff, I would recommend just using S3. Even if you're not hosted on Amazon, I would say that S3 is really a great solution. It's a difficult problem to solve yourself. Even if you're hosting on some other cloud or in your data center, I would definitely consider S3 as file storage. And then we have some less common types of states that you may have on your servers. So we have logs. As your application grows, as you have more queue workers, crons, backend processing jobs, you will need to coordinate. Like these processes will need to be able to figure out what they are allowed to do so they wouldn't step on each other's toes. So this kind of state obviously cannot live on your web servers. It cannot live on your backend processing machines. It has to be pushed out to some data store as well. I would recommend really using some open source library for that, and pretty much any data store will work. If your data store supports atomic operations, you can implement some basic locking functionality on top of that. So again, same kind of data stores, maybe Redis, a little bit preference towards Redis. And the last type of state that I would want to mention is temporary data. So all sorts of cache, temporary files, counters, whatever you may need to process, like to calculate in your system. This stuff, you will have to be careful. You will have to decide, can it live on the, let's say, web server? Can it live on the cron or whatever queue worker machine? If it's disposable, if it's not really necessary to be able to serve the next request, then yeah, it can sit on the server. But in some cases, you may not be able to keep it there. So these are like the main types of states that you may face. And let's quickly just talk about the benefits of why would you bother paying attention to state, managing it carefully, getting rid of it on your application servers. So the main benefit of keeping your server stateless is that it makes scalability really, really easy. So for all types of web servers, web service boxes, you just put a load balancer in front of that, register your machines with it, and that it is. So if you're on Amazon, you just configure Elastic Load Balancer, and you don't even need to have another instance for stuff like Nginx or Varnish or whatever. It's up to you, you can use it, but either way, scaling will be really easy. The second benefit is that failure of a particular server will not be an issue anymore. There is no drama that, oh my God, my server crashed. You just lost one server out of the pool. It doesn't store any information, it doesn't have any data, no one gets logged out, no one lost their checkouts. There is no problem when server goes away. And this is the same with deployments. You will be able to just take your server out of rotation, upgrade software, or do whatever maintenance you need, put it back in, so deployments become much easier, and you can do it during business hours. And finally, if you keep your web servers stateless, you can also automate scalability. So like already some speakers mentioned, you can set up something like auto-scaling on Amazon or whatever other hosting provider may already have that. So this is just automated process of provisioning more machines, adding them to the cluster, or removing them from the cluster based on whatever the schedule or based on some metrics like CPU and stuff. And you will be able to do it because each of these servers is identical, like they don't have any data, so you can take it away or you can add more. And the only place that you need to update is the load balancer. The machine or the component that's distributing the traffic, that's the only place that needs to be aware of which machines are in the cluster. So anyway, that's enough about state. Let's talk a little bit about the scalability techniques that I mentioned. So there are three underlying scalability techniques that I would like to talk about today. And each of them have different benefits, different challenges, and they are applicable in different situations. The good thing about them is that you can really mix and match. You can use them all together or just one of them. And you also see the different data stores or different systems apply these techniques in different ways, like together often. So these are scaling by adding clones, functional partitioning, and data partitioning. So let's have a quick look at each of them. So the first one is scaling by adding clones. And how it works is, this is really related to the states and stateless servers bit. So all you have to do, you have to make sure that your servers are interchangeable, right? So every single server in the cluster is identical. It doesn't need anything special. It doesn't have anything special. Any request or any queue job or whatever you're doing can be sent to any of these servers, right? This gives you flexibility, and this allows you to scale more easily. So the benefit of scaling by adding clones is that you can add servers to your stack. You can remove servers from your stack, and there is no really any challenge around it. If you want an analogy, you can think of scaling by adding clones as thinking of your servers more like chickens rather than cats. So you don't give them names, you don't get attached to them, none of them is special. You just have a pool, you have a farm of your servers. So let's have a quick look how scaling by adding clones looks like. So we have a pool of stateless servers in a cluster. We put a load balancer in front of it. The load balancer is aware of the state of each server, and it distributes traffic at random to any of them. And again, scaling up is as easy as just spinning up another instance, installing the software, registering it with the load balancer, and that's it, really. Scaling through this technique is really simple, and I would definitely recommend it for pretty much anyone. There is not much complexity or challenge related to that, and it's really the best practice if you're hosted on Amazon to go this way. The second technique is a very different thing. It's not as much about scaling your infrastructure. It's more about scaling your architecture, scaling your company, your teams, your code base. So as your company gets bigger, you cannot depend on every engineer working on the same thing. You will have to find a way to split things up into smaller bits. So how functional partitioning works is really that you want to isolate part of the system and create a subsystem out of it, independent, either call it microservice, call it web service, call it whatever you want. Just something that encapsulates a small part of the functionality and can hide the implementation and the details of how this stuff is done under the hood. The benefit of functional partitioning is that each partition becomes like an independent product. So now this is the scalability bit that you can now have a separate team responsible for that product, for that system, and they can deal with the complexity. Everyone else in the company can just learn the API and they don't have to know the details. The second big benefit is that now you gain some flexibility, some extra freedom, because each of these subsystems could be architected differently. It could be solving scalability problems in different ways, maybe using different technology stack, maybe using different data store, or modeling the data in different way. So you gain some freedom there. And how functional partitioning looks like is usually just by dividing your system into smaller subsystems. Usually web services or whatever, microservices. So if we had an e-commerce website, like a shopping cart kind of system, we could imagine that we would split it into two smaller subsystems, one controlling the product catalog, where you see all the products, the prices, you can search for them and whatnot. And another part of our system would be focusing on personalization. So it will be storing all the historical data, clickstream, purchase history, all the kind of user-related information, and then it will also run some magic artificial intelligence algorithms to try to make sense out of that. And as you can imagine, these would be very different use cases. They would probably require a different approach to solve scalability problems, and this is how it comes really handy. So how we do it, you just create two different types of clusters, put load balancers in front of each of them, and you can scale them. You can scale each of them independently now by adding clones, assuming that they are all stateless anyway. So now the third technique is data partitioning. And I was talking a lot about making sure that your web servers and your whatever application servers are stateless, but this is just deferring the problem, right? So I have my web server, I have my web service machine, I have my queue worker, and now I'm just pushing state out of them, right? I'm making sure that they are all stateless, but this state has to go somewhere, right? So eventually you're faced with the challenge of scaling the data layer, and this is really where data partitioning or sharding comes in handy. So how it works is that you try to find a way how you could divide your data set into smaller groups, into smaller buckets, smaller chunks. And then you find whatever data store or approach that would allow you to distribute this data across multiple machines. So none of your nodes, none of your servers have to deal with the entire data set anymore. Each of them is responsible for just a smaller subset of the entire database. So what you gain out of this is really horizontal scalability of the data layer. And this is probably like the main challenge from all of these things that we're talking about. It allows you to buy cheaper servers. So something like guys were talking about Elasticsearch, right? By using sharding, by using data partitioning, you're allowed to have, let's say, 20 servers, which are all cheap, with reasonable amounts of memory, and you can still handle the workload. And what's even better is that you can just keep adding one server, two servers, depending on your requirements. And the last one is that it gives you, well, not infinite, but horizontal scalability in context of I/O, which I/O was always like a challenge in the data layer. So you can increase the throughput, the concurrency, how many writes, how many reads your application needs to do to the data store. Let's have a look at a simple example. So data partitioning can be done in many different ways, probably in every application. And the main challenge, the main trick is how do I divide this data set into smaller bits? So in a very simple, a very simple way to explain that is, for example, if you had an e-commerce website, like whatever platform where you can subscribe for an account, and you can open an online shop, right? So we are a platform, we are letting people open their shops and sell their stuff. So if we kept everything in one database, eventually we have thousands and thousands of shops. Each of them have users, a lot of items. We can't fit it on one machine. So we could decide to divide partition the data set in some way. We could, for example, come up with this idea that anytime user registers for a shop, we, by random, assign him to one of the shards. They get an ID, and anyone who lives in the shard 1 gets the odd numbers. Everyone who lives in the shard B, they get the even number or whatever. The point is that now every shop belongs to one of the shards. So each account, each seller, or each online shop entirely, with all of its data, all of its purchase history, all of its items, lives on just one of the databases. So you, by doing that, you automatically allowed your application to double the capacity on the database layer, right? So you don't have one server, you now can have two. And then by the analogy, you can add more and more and more servers. Just it's a little bit more complicated most of the time. So the tricky bit here to remember is that anytime that you want to actually access data of particular shop, you need to know the shop's ID, right? Because we decided that every shop with the even number lives on the shard 2. So anytime you want to run a report or you want to access the page or buy an item, you need to have the shop's ID, because this is the only way how you can find on which shard this particular account lives. So that was like a really quick introduction to these techniques. Let's talk a little bit about challenges, because each of them has some challenges. Luckily, like I said, the first technique is really, really easy. If you keep your servers stateless, scalability is a piece of cake. So literally, I don't really see challenges. This is like the best practices of Amazon hosting anyway, and probably if you're running any servers or EC2, you would already know by now, or you should definitely start looking into it, that your EC2 instance has to be stateless, cannot have any data on it. Everything else has to be pushed out to some data store or whatever, shared storage. The only challenge that I can imagine with scaling by adding clones is maybe cache, maybe some data that you thought it would be safe to keep it on the web server, but then you realize that it's not really safe. So for example, in the e-commerce site, maybe you're caching the product metadata, and you figured that it would be safe to just keep it in memory, in APC, or put it on a file or something like that, or shared memory. But then what you can end up with is that your request goes to one server, and you get the price, whatever, $10. Your request goes to another server through the load balancer, and then you have a different price, the previous price, right? So in some cases, it's okay to have different cache values on different servers, but some applications may not allow you to do that. So again, scaling by adding clones for stateless components, easy, definitely should do it. For the stateful components, I think that's really a danger zone, and I would strongly advise against doing that. So either deploy your code to the server or keep your data on the server. You shouldn't ever mix them up, right? Databases are trying to solve these problems of replicating data and synchronizing data and figure out consistency on all these challenges for decades, and it's still not working out so well. It's still a challenge. So again, where this is applicable is any server that has your application code. Then functional partitioning, there are a few challenges. I think the main one is, and that was also mentioned in one of the other talks, is the complexity. The stuff that people get so excited about, the microservices, and it's so cool, and you can run 50 of them and whatever. Yeah, it's cool, it's fun, but it's much more complicated. Rather than having just one cluster with 30 servers, now you have 50 clusters with 2 servers each, but they all have different configurations. They all have dependencies on one another. They all have different whatever requirements. You have to manage all this stuff. So I would really be careful about going too crazy about functional partitioning, especially if you have a smaller team. Like if you don't expect your company to grow to 100 people, maybe microservices is not really the good way to go. Maybe you have 2 services, but not 20, not 60. So another challenge of functional partitioning is that your data may become disjointed, and what's even worse, it may become inconsistent and redundant. So each of these microservices, let's go back to the e-commerce site, right? So we have the product catalog and we have the personalization service, right? So now we can easily imagine that we take the purchase data and we shove it into personalization database, and we want to capture some stuff like maybe a price or like a product ID, maybe product name or category or whatever, some other information. But what do we do when the product is updated or if the product is deleted from the database? Do we have to go back to the other service and let the guys know that they have to update all the records? Or maybe we don't care. Maybe it's okay that we have like a snapshot, like an archive of this information from purchases. So even that it may sound like a simple thing that, oh yeah, I know, we can do it this way. But if you have 20 microservices and they all are modeling the data in different ways, and they are all storing the data in different places, and they have some business rules around it, it can become really, really difficult to figure out what's the right thing to do. Like, what do we do with this, right? So disjointed, meaning you have data in one service, this data in another, you can't join it, you can't run queries across these services, and inconsistency and the redundancies about like the same data being in different places in different forms. So I think this one is quite tricky as well. Well, the next two maybe are a little bit obvious. So you will not be able to scale using functional partitioning, right? It's not like horizontally scalable kind of technique. This will not allow you to have thousands of partitions and each deployed on different server. Maybe you can have 10, maybe you can have 50 if you're really a big company, but this is not something that will let you just keep adding servers by itself. As you add more of these microservices or whatever you call them, these partitions, you may also expect increased latency because now you're adding more layers in the call stack, right? So your front-end machine will be calling a few web services, and then the slowest response will be holding everyone back, and you're adding the complexity and the time needed to process responses, requests, network latencies, all this kind of stuff. So that could be some kind of challenge. Yeah, oh, and the last one is that obviously it's going to be difficult to add it to the existing system. So if you have an existing system, maybe not even legacy, maybe a nicely designed system, it's probably going to be really hard to split it into smaller chunks and make them really independent partitions. And the third technique, the data partitioning, I would argue that is the most difficult one. And I would argue that you shouldn't do it unless you really, really, really have to. And how do you know that you really, really have to? I don't know how to tell you that. So I know that it's exciting and it's cool and it feels like, you know, oh, let's do it. Maybe we'll need the sharding or whatever. But you're going to go into a lot of complexity, into a lot of more headaches. So I would really argue that you should defer that until you really need to. Like, there's no way you're going to be able to support the read-write throughput and the demand on your databases. There's no way you can add caching to solve the problem. There's no other way. You have to shard. Okay, fine. So the challenges that come with sharding, the first one is uneven data distribution and uneven load distribution. So you may imagine a scenario where you're creating a database of users and you're deciding to which database user belongs based on the country of origin, right? So then you may end up with one database or one shard that got Luxembourg and is super happy because there is nothing to do, 10 users. And then you get the other shard which was unlucky to get China or India or some other huge population, and now suddenly it gets overrun. You're not able to handle that. And now you're in trouble because you have to find a different way to shard your data, and your whole system is already coupled, built around this. So this could be a really big problem if you do it wrong. The second one is the uneven distribution of the load. So hotspots, basically hotspots. You may have, again, going back to the example of the e-commerce website, right? You have different shops. You distribute shops around different database servers. And now one of your shops is running a promotion, a sale on iPhones. They are giving iPhones for $10. So you have huge traffic coming to this server. And then it gets featured on Facebook and it's featured on whatever, Yahoo or I don't know where else. And your server goes down, right? So again, data partitioning difficult. And if you shard incorrectly, you're pretty much screwed. It's going to be really hard to reshard your data. Another challenge that, I don't know, maybe obvious, maybe not obvious, is that working across shards may be challenging as well. So when you're deciding how do you want to partition your data, you have to make sure that you will never ever have to talk to more than one database to run your query. So for example, the example with e-commerce where we have one seller or one shop belonging to one database, that sounds like a reasonable choice because I will never run sales reports across two shops. Well, it's unlikely, maybe some internal reporting or whatever. But maybe you can deal with that in some reasonable way. Users would never need that. Users go to one shop and all the data for this shop sits in one place, so you can run reports, you can aggregate, you can check the stock or whatever else you need to do in a reasonable way. But if you ever had to run queries across shards, then it can be a real challenge. Yeah, I already mentioned that if you're doing data partitioning, you always need to have the sharding key at hand So if you're sorting by the country of origin, well, you have to know the country of origin for everything you do. For every request, for every queue job, you can't run a query without it, right? You can't be querying all the servers and trying to find out where does this user belong. Again, something that I already mentioned, maybe in a way, is that rebalancing of your cluster is pretty difficult stuff. So I would definitely recommend not doing it yourself. If you, for example, need to use MySQL, I would say probably not great idea to use data partitioning, because you will have a lot of work. Like if you need to move some portions of the data between servers. If you want to add another server, well, somehow you have to move this stuff around, right? Someone has to move the user accounts or the whatever seller accounts onto this new server to use this capacity. So doing that without outages, with consistency requirements that you may have or whatever, not missing any data, that can be really hard. So I would recommend only depending on the data store to give you this functionality. If you're using something like Elasticsearch, whatever, Cassandra, DynamoDB, whatever data store that can handle rebalancing the cluster, whenever you add servers, it can just move stuff around and the cluster is happy. But don't do it yourself. And now let's go through the scenario. So like I said, we'll go through like a little hypothetical application to see how we can apply these techniques. So let's imagine that we are building an online radio kind of app like Spotify or Grooveshark or whatever. And the main requirements of the application would be to have a catalog of songs, albums, artists, and all this kind of metadata, obviously. So users can search for their artist or the album or the genre or whatever, filter information. And we also need some functionality around the user. So they need to be able to favor songs, they need to be able to create playlists, they need to be able to maybe share these playlists and listen to the music, right? So if you look at these requirements, it doesn't sound too bad, but if you now had to design that for, I don't know, a couple 100 million users or thousands of concurrent users, that can be much more difficult. So let's imagine that we are actually faced with this problem. And I thought about it for a while, and I thought that maybe maybe creating a functional partition like that would make sense in this case, because it seems like we would have two different sets of requirements. So we would have the catalog service, the stuff that has all the songs and artists and allows you to search, like auto-completion and full-text search and filtering, all this kind of stuff. And then we would also have the user service or user profile service that will have requirements focusing more about writing a lot of stuff, like unique bits of data, and reading a lot of unique random bits of data. But it will not require us to search, it will not require us to do other things that the catalog may need. So let's go through each of these sections and talk a little bit about this technique. So first of all, so we have the functional partition. We found a way where we could cut the system into two smaller bits with fairly well-defined requirements. And we feel that we can probably make them fairly independent as well, that there will be not much overlap of the data and the functionality. So the first area, let's look at the user profile service. So again, like I already said before, we keep our application server stateless. So we just put a load balancer in front of that. We add a bunch of servers, deploy code, easy. Horizontal scalability in this particular cluster just by adding clones. Then the more challenging bit of this service would be the data layer, right? Because as I said, if we had thousands of concurrent users and they all need to load their playlist and they are all favoring stuff, so there will be reads and writes, and maybe we also need some historical data of how many times they listen to each song because we want to build their profile and mine the data. So it feels like there will be much more writes going into this service. So I kind of thought maybe it would make sense to use something like DynamoDB or Cassandra. So a data store, NoSQL data store, which provides horizontal scalability functionality kind of out of the box. So it takes away the burden of replicating the data, sharding the data, moving data around. If a server dies, how do we handle that? If we need to add some servers, how do we redistribute the data, like balance the cluster, all this kind of stuff. And I put Cassandra over here just to highlight one more feature that I really love about Cassandra's design, is that Cassandra nodes are actually interchangeable from user's perspective. Even that we shard the data, and this node doesn't have all the data that this node has, from user's point of view, they are interchangeable. You can connect to anyone in the cluster, and you can ask, give me data about this user. And this node will figure out where does this data live. It will figure out which nodes have replicas of this data, if they are alive or not. It will take all this burden off you, and it will just figure out, okay, the data is here, so I fetch that, and then I give you the data back. So you gain more flexibility here. You can put another load balancer in the front of that, and you can add all of your Cassandra servers into the cluster. And now these guys, they don't even know who's actively running, which server is working, which not. You can completely hide that from your application layer. So I think that could be an interesting way to approach this problem. Cassandra will allow us to scale by adding clones and data partitioning. Adding clones means replicating the data. So you can say, I want 4 copies of each bit of data. And then it means that I can scale my reads, right? Because my data lives here, 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 and here for a particular user. So I have more of a chance of hitting the server that has it and reading it and whatever. And I can also tune how I want to partition the data in my application and then distribute it across the cluster. So horizontal scalability through both of the techniques. And now we are moving to the catalog service, right? So like I said, this will have very different requirements. And I have a feeling that it will be mostly read-only data, right? Like realistically, how many times the song will be changing, the title will be changing, or the artist's name will be changing? Pretty much never. So I'm kind of thinking we could put reverse proxies layer on top of our application, or maybe even use like a cloud service like whatever, front cloud or whatever other hosting reverse proxy kind of system. And offload most of the work to this layer here. So these are very dumb proxy servers like Nginx, Varnish, or whatever else. And they are not really doing any computations. They don't have application code installed there at all. So they are very easy to replace. They are easy to, like you barely ever have to redeploy this stuff, right? They just sit there. And the benefit again is that you can scale by adding clones. These guys, we just use HTTP headers to decide how long each piece of content can be cached for. We have a pretty good feel that they will be changing rarely, so we are okay with this guy having different version of the cached object than this guy. For example, we cache a song title for a day or an hour or whatever. And we don't care that you may flip, depending on which servers you hit, you will see a different title because there was a typo or something. So then we can scale this horizontally by adding clones, even that there is some kind of state, but it's disposable. It's not significant. Then we move to the application, layer, and here again we have stateless servers. So we can scale this layer by adding clones, and again we can keep adding servers, as many of them as we want. This is where our business logic will live. And when we go to the data layer, things get more interesting now. And there are some decisions that you have to make depending on how big the data set is and what the usage pattern will be like. I'm kind of thinking that if we only have the catalog of songs, albums, and artists, and iTunes has just like 26 million songs, maybe we can have it on one shard. Maybe we don't need sharding at all. Maybe we can just say, I want 3 replicas of my Elasticsearch whatever data set, but I don't need to shard it. I don't know if it's a good idea, maybe not. We would have to look more into it, but it's just an idea, right? That you decide what, based on your requirements, your challenges, your data set, your traffic patterns, you choose the technology that fits and you choose the actual techniques that are necessary, not just do it because it's fun. Because actually, if you're sharding, depending on what technology you're using, sharding may be more expensive. If you have to talk to multiple servers to run the query, for example, the search across 2 servers, and then they have to be merged and you have to get the final response, maybe it's better to have one shard. But anyway, so we would have some kind of search index like Elasticsearch to do all the auto-completion, full text search, all this cool faceting search stuff that guys were talking about. And then we may also have some other data store. In this example, I actually used MySQL, just for the sake of it, just to prove the point. I don't know if MySQL would be good, maybe Mongo, maybe anything else. It doesn't matter. I thought MySQL just to show a different approach, that's just to show a different scalability model here. I'm kind of feeling that we would offload most of the work here. There would be not so much to do here already. So maybe the queries that will really go to the database wouldn't be a problem. And it would be many reads. So maybe MySQL can handle it as well. And it's not a huge data set. So if you can get like 64 gigs of RAM, you can probably get it all pretty much in memory. I don't know. So the interesting bit here is that we have a load balancer. But the load balancer is only talking to these guys, the read replicas. So in MySQL, you can set up replication, that you have a master server, and the data is replicated to all the slaves. And then slaves become interchangeable, right? Every slave has the full data set. You can talk to any one of them and run your queries. So we could have a load balancer configured to talk to all of these. But for writes, we would actually have to go through this explicit path to the master, because you can only write to the master server. I'm not saying this is perfect. I'm not saying this is a good idea. Maybe we should have sharding here. Maybe we should put a load balancer here so we don't need to know about the structure of this cluster as well. It's just an example. It's just to illustrate how much freedom do we get applying these techniques. And now, if you look at this again, you will see that we have some green boxes, we have some yellow boxes, and we have some red boxes. What they mean is that the green box is fully independent, it's fully hidden from any clients. So if I need to deploy a server, like add a new server here, I don't need to change anything anywhere in this whole diagram. I just need to update the configuration of the load balancer. If I lose a server, no one else has to know about it. I need to update the load balancer. If the server dies, the load balancer just figures it out based on the health check. So that gives me a lot of freedom. Now my clients, they only talk to the load balancer. They don't know that my server is, I don't know, dying, or I add another server. I don't need to update them. They don't know the IPs. They are not coupled in any way. And the same situation here. None of my servers need to be updated if I added a new class, a new node, right? I add a new node. I say Cassandra, rebalance the stuff. And the new node is available. I register it to the load balancer, and that's it. I don't need to deploy new configuration. I don't need to do anything else. This is self-contained here, which is good. Same story here. We have a load balancer. That's the only component that knows. But with the yellow bits, it's almost as good, but it's slightly worse. So horizontal scalability is still not an issue. But now if I add another web server, I have to update configuration of all of my proxies, because my proxies actually distribute the traffic. It's not a load balancer. In this setup, Nginx has the list of the IPs of the servers which are in the cluster, and it will distribute traffic across them, and it will figure out that this server is down, so okay, take it out. But there is no load balancer in here on like a network layer. So anytime I add a server or I remove a server, I would actually need to probably update configuration on all of these. And the same history here. If we didn't have a load balancer, if I want to add another server or it died, I would need these servers to be able to handle it, either by updating them or having configuration somewhere else externally. And with MySQL, it's the worst bit, because not only it's trickier to scale, but it's much more difficult to scale the the master. You really have to know which server is the master. Your application has to know what's the master, and recovering from loss of a master is much more complicated. So I hope this wasn't crazy talk. And we have time for some questions. Oh, I'm 4 minutes late. Sorry for that. Questions?
Speak up.
Don't be shy. I'm a very approachable person.
Doesn't usually bite.
All right, we have a winner.
How do you actually scale MySQL master?
Master?
Yeah.
All right. So it's tricky. You can do bits of it, but there is no silver bullet. So MySQL replication is good for reads. You can scale reads, right?
Yep.
If you don't write a lot, it will just trickle down to all of your reads replicas, and you can read as much as you want. You can add more servers. So you can have throughput on reads just by adding read replicas. On the master, there is not really so much you can do, because even if you set up master-master replication, which we actually run at Yahoo, but it's just for high availability reasons, you will not gain any performance improvement, right? You will not gain any scalability. Because if I had another master here and I set up master-master replication, I didn't make anything better. Each of them has to write everything anyways, right? So I still have to have all my writes stream to this master, and it will replicate to the other guy, and whatever writes come to the other master, they have to replicate here as well. So you're not gaining anything. I would say it's just worse. So we have master-master replication just for high availability. So if I lose this guy, I can very easily switch to the other one, and I have a pool of, like, let's say, 4 slaves here, 4 slaves there. So yeah, it's inconvenient. Someone has to log in, do some commands, but I don't really have a big deal. How you really horizontally scale MySQL? I have an example in my book, so I would refer you to that. But now for reals, you can do it in your application layer, right? So you can write a bunch of code that will distribute your data across multiple machines, multiple masters, and then have slaves connected to each of them. But this is difficult. You can do it through, for example, setting up actual logical MySQL databases way ahead of time, so then you don't have to reshard. So for example, you think you will need up to 32 master databases, right? So you start off with 1 physical server, but you create 32 databases, like shop 1, shop 2, shop 3, shop 4, shop 32. So you have 32. And now scaling is easy in a way that you bring up another server, right? You copy the entire data set, and then you drop half of the databases on this side and the other half on the other side, and you rewire your application that it would know. If I'm in the database shop 1 and 216 or whatever, right? I need to go to this master. If I'm talking to the other bunch of databases, I go to the other physical server. And then you can split it by half again, I mean double the capacity and double the capacity, but it's much more difficult. I don't know, I wouldn't really recommend it this way.
So it's back to...
But I've seen a system done this way, sorry. Huh? Yeah, so it will work, but it's a lot of work, a lot of extra work. That's a good one.
Cool. All right, we've got time for one more quick question.
Thank you. So when you're architecting a solution like this, where you've got all your services split out into microservices, what does your dev environment look like? How do you set up a dev environment that's going to let you sort of replicate this?
That was my first thing that I said on the slide with data partitioning, right? And functional partitioning. Doing it too early is an overkill. It's a disease. You shouldn't be doing microservices if you're not going to have 60 engineers, 100 engineers, or whatever. It's going to make stuff harder. Yeah, you can have your Docker images. You can probably wire them by linking or whatever and make it easier, but you're still going to have much more stuff going on. So yes, your development environment is going to be much more difficult. You're probably going to have to replicate whatever are dependencies of the stuff that you're working on, or have some shared setup. So for example, you have, I don't know, the e-commerce example, right? You have your, oh, I don't have the slide. You have the product catalog, you're working on that, but it depends on some other microservice. Well, so you need to have some maybe shared instance for all of your engineers of this particular component, so you just configure your machine to talk to that. Maybe that's an option. Or you have Docker images and you run everything, but it's much more stuff to worry about. Give me more. Anyway, if you have more questions, you can grab me after the talk. Come talk to me. I'll give you the business card. Send me an email. You can win the book and have a coffee with me. So thanks a lot, guys.
Thanks, Arthur.